All right, so this could take a little while because I'm going to take a sneak preview of new material once we come back from midterm break. I think for the purposes of grading, we've got 75% of the term in front of us, and in the next 3 days after the break, I'm hoping that last 25% is introduced, and then we play with it until the end of the semester. I won't grade on anything more than the topics that I want to introduce here. But if somebody is able to learn more and processing all of this stuff, then not gonna put the brakes on. Continue to put problems at the end of the lesson set into the newer material. So some of what we're going to do in the second half is deepen our understanding of some topics that are already in front of us. We try to do that with every topic, but focused depth on in a few areas. So I guess I don't have to say much more than that other than to get into the new topics. Some of them are really not new. First one I want to talk about is average rate of change. And most of the worksheets that I'm writing are designed to allow a student to not have foundational difficulties in calculus. And this is a problem that a calculus teacher shouldn't have to spend time on. And yet when I was teaching it, it took a couple of days before students were able to, oh, that's what that is. And it's really an Algebra 1 concept. And we did it a couple of weeks back. I just forgot to keep putting it on the lesson set. So I won't now. So here's an example of average rate of change. This one I at least knew was going to start us off on our discussion. So here's y equals x squared, a couple of points. And all average rate of change is the slope connecting those 2 points. It's Algebra 1. So if somebody asks for average rate of change, they're looking for the change in this function, y equals x squared, from -2 to 3. And we've certainly done this with linear functions all semester. So -2, 4. I think I did 416, sorry. 416. So I guess I'm doing -2 to 4. I changed that because I wanted something a little different than a 1-to-1 ratio. So we're going up 12. We're looking at 6. Looks like it's 2 to 1. And this is called the secant line. I don't even know why it's called that. I probably should look it up. But it's connecting the 2 coordinates, and all you're doing is finding slope. Now, in a calculus class, that changes to finding rates of change at an instant. And we're still talking Algebra 1 here. We're going to do it from an Algebra 1 perspective. And then we're going to at least plant some seeds around derivatives, because students get to calculus and, my God, it's not rocket science. And we can introduce some of these concepts early on because math does take time. It does take time to digest. In fact, I did put something over here. Come on, Renee, let's go down over here. Yeah, so while I mention that, at least say math concepts as we move up the ladder take time to digest, and they become more challenging. Each level, in the same way, you have more responsibility as a person as you get older, and you're trying to make those transitions into being responsible now, and you're getting lessons at learning how to be responsible. One of those lessons is spend time on what you're working on so you can try to learn it and understand it, and it takes internal motivation. So 2 + 3, I don't think that in grade school you had pictures to look at. And you can count things, and memorization of tables and adding fractions. Well, that you start to get into a little bit more challenging concept. And this is where you start losing some people. And I don't know if the drawings were done for you. A lot of people had trouble adding and subtracting, multiplying and dividing fractions. That shouldn't happen at the high school level. And yet it's a difficulty. And I don't blame the student. I blame the process. So I don't know if you saw drawings like this. There's other ways to teach addition of fractions, but it's a rule that you have to have addition. You have to be able to add like terms. Well, these terms are not alike. This term is divided by 3. This is divided by 2. So we got to get something that there can be pictured in the same sort of sectioning off into amounts. Of course, that's sixths, right? You can see a half is 3/6, and you can see that 1/3 There's 1/3 up here, so boom, boom, 1/3 is 2/6, right? So here's the 2/6, and that's 1/3 of the circle. That's 2/3 of the circle, and that's 3/3 of the circle. I broke it up into thirds, right? And that third is 2/6. Now, if you write that, 1/3 is 2/6, and 1/2 is 3/6. Well, now you have 6, and you can say that that's 5/6. All right. So yes, concept got a little harder, maybe in 4th grade, 5th grade. Well, it's going to get harder more. It's getting harder right now. Takes time to digest concepts, but we're building off of something that everybody should know at this point. I put a 0 in, I square it, I get a 0. I square 0.01, I get 0.0001. And now we're talking about change at an instant. And I'm just gonna take 2 decimal places and divide by 2 decimal places. I'm going to make the numerator the same number of decimal places and say, well, how am I changing at this instant? I don't think I am. I think I'm flat. I don't think I'm really going up at all. If you divide something into 0, you get 0. And it just happens that y equals x squared, the rate of change, right? This is a continuous function. I'm just talking about n instances. That's a 1, that's a 2, that's a 3, and we have tabular support to give us a feeling of how are the table values changing at x equals 1. Well, you put it in a calculator, 1.001, you get 1.02001. And if we get rid of those 3 decimal places, divide the change by the 3 decimal increment of 0.001, we can see we're going up at 2 to 1 at that instant, going up at 2 to 1. And if we did 4 decimal places gets us 0.0004. We'll get rid of those. We'll divide the change by 0.001. You're going up at 4 to 1. And we've got the proof here. We've got the numerical. We've got the visual. And if you look at 3.06, so 3 links with 6, 2 links with 4, 1 links with 2, 0 links with 0. 0, 2, 4, 6. You know, I think it's going up at 2 to 1. Whatever the x value is, I think it's doubling. 1, 0, 1, 2, 3. I think I'm doubling the 3. I'm doubling. And we're going to look at that in more detail. We're going to draw squares. We're going to talk about the new layer of area. We're going to do all that stuff in the second half. How does it help us? Well, it's an entry-level derivative at the calculus level. We don't have to do much more than that. But stuff we're working on, concepts we're working on, will help us understand what I'm going to do over there in 2 minutes. Now, we're working on this piecewise function. Yeah, we're somewhat successful. We're about halfway there with the class. All right, I'm seeing more and more detail that's correct. That's not wrong, but we haven't finished the concept at all as a class. Got a half a dozen people who can do it in their sleep now, and trying to get more people in that category. So you got a V shape up, but I'm going to take this to a little deeper level now. All right, I can see 5, 7 as the vertex. I hope you can. And so I drew it over here, V shape, 5, 7 with the vertex. I like the y-intercept, so I substituted x for the value 0 with the value 0, and I can see that I got 37 units come out of that calculation. And I know this arrow is pointing from right to left, but kind of ignore it. Try to ignore it and ask, what am I doing? What's the average rate of change? Yeah, that's good. What's the average rate of change? Well, it's constant rate of change here. So it doesn't matter what 2 points I pick, that's a constant change. And what is it? Well, I hope you're saying, how do you get from 37 to 7? You're going down 30. How do you get from 0 to 5? You're changing by 5. And it looks like that slope is -6, and it passes through the point 5, 7. We're good at that. Everybody's capable of doing that. Now, are you capable of making the connection? Oh, Geez, next time I look, I wonder if that's a big clue as to what the rate of change is. And of course, if I follow my finger down and then up, well, then this one's going to be 6x minus 5 plus 7. And we've talked about x minus 5. X minus this part of the 3 times x minus 5. All right, but I'm just concentrating on x minus 5, and 5 gets me 0. And what happens if I slap an absolute value on that? The negatives become positive, and so this hinges at x equals 5. And there's what I'm hoping to see everybody be able to do by May 15th. Of course, leaving your worksheets here when I write out an answer key that took an hour and a half to write out, which I didn't have to do for myself. I could have just looked at the problems and probably done better without writing them out. And seeing 4 packets left in the room on Friday is a little disappointing, considering the progress to making yourself have a successful term really rests on learning from your mistakes. And I don't know what you were practicing over the weekend. I'm sure you were looking at the videos. Yeah. Well, for those of you who aren't getting this right now, I'm telling you, that's why. That's why you're not getting it right. So for the 4 of you who left your packets here, that's why you're not getting that right. I'm just telling you like it is. I'm a product of the 60s. Oh, I think I was there. Yeah. All right. So why am I highlighting this right now? Because it blends into what I was just talking about over here. All right, so let's get over here again. Renee, you're going the wrong way, buddy. Spin you around. It has bearing on your ability to understand the following. This could be a long video. So, could I talk about this as rates of change? I'll use this terminology for right now. Could I really be talking about change in y, change in x in terms of at a moment? Because I think we just proved that the rate of change of x squared is 2x, and I'm actually multiplying that by a 2. I think I get 4x as how this term is changing. And I think that this is always going down at 20 to 1. And I think a parabola has a slope of 0 at its vertex. And so if this is a slope, I'm trying to describe this at every instant. I wonder when it's 0. Sure looks like it's when x equals 5. And there's more things we have to do to prove whether something's a max or min, but we don't have to talk about that right now. We can just look at this and go, oh, I got the number 5 differently than how? Well, I hope your brain just said minus b over 2a. Positive 20 over 2 times 2 is 4. That's 5. Oh, another one of those coincidences. We just seem to be stepping over coincidences. So there's any real reason I can't do that right now? No, because I already just did. Okay, and it's important for you to have more time to digest concepts that become more and more difficult as you move up the ladder in this discipline. So I just planted a little seed, and I'm not going to grade anybody on a derivative, but I am trying to set you up for success in your future classes. I am trying to get you to think mathematically. Okay, so what are some of the other things that we're going to be looking at? Let me erase as we go. So we just talked about instantaneous rate of change. And I think that's an Algebra 1 perspective. I don't think I did anything there that was deeper than early algebra, change in y or change in x situation. So we're going to establish the rules of logs. We already have. Whether you realize it or not, we've already done that. We've already looked at the ln of 2 plus the ln of 3 equals the ln of 6. The question is, you may not even realize it yet because it was done in class like I'm talking now, and it takes focus and practice. One thing I definitely know is we haven't had practice with that, a lot of it, but I have put it in front of you. Now, when do you add exponents? When would I add 0.7 and 1.1? Those are what I asked you to memorize for that. When would you add those? I think when you did e to the 0.7 times e to the 1.1, I think you add them. And it sure looks like that represents 2, and that represents 3, and that represents 6. It's got to. 2 times 3 is 6. So What's that tell me? That tells me that I'm multiplying the quantity 2 times 3 in this problem. Okay, so that's the ln of quantity 1 plus the ln of quantity 2. Right? What are those quantities? Those quantities are these numbers in this instant. And I know what 2 times 3 is. It's 6. So what's that tell me? My first rule of logarithms? Addition of exponents implies multiplication of quantities, and there's the implication. You might ask, well, how about 6 minus 2? And I hope you would say 3. Because ln of 6 is this, and if I do minus, well, let's see. 6 divided by 2, let's do the same thing. 6 divided by 2, oh, that's e to the, we just said 1.8 over e to the 0.7, and I think that's e to the 1.8 minus 0.7. That's the rules of exponents that govern those quantitative divisions. And I do believe that's e to the 1.1. Sure seems like subtraction implies division of quantities. And so when I look at, remember, this is exponent 1. There it is. There's exponent 1 minus exponent 2. There it is. Exponent 2 gets us exponent 3, which is, right, 1.1. And that came from this division statement. So there's your second rule of logarithms. Your third rule of logarithms. Log, I'll switch to base 2. Might be easier to see this one. Is equal to 3 log base 2 of 2. Those are true statements. And so is log 2 of 2 to the third, which is really a 1 and a 3 on the outside. I'm trying to hope that you can see 3 times 1. Well, here's that 3 times 1. And what do I refer to this as? Power to power. Power to power. You're more familiar with m squared to the third. What's that power to power? M to the sixth. Okay, so what can I do with a problem like this? I can take the 3, and I know that it's the same as that. And so we'll be covering the rules of logarithms, starting up with that. Oh, did I say we will be? I'm sorry, I should say we just started the rules of logarithms. So you can try to solve a classic equation right now. Get us up and running with the rules of logs. How about you try to do the following? Log base 2 of x plus log base 2 of x minus 2 equals 3. You pause the video and try to solve that. And this is going to go on forever because I'm introducing all of the things that we're going to be working with. Well, I think based on what I said 5 minutes ago, I can multiply those and write it as what we call a single log expression. Quantities multiplied. What is 3? It's an exponent. Exponents go on top of bases. So I'll do the inverse of log base 2. The inverse of log base 2 is 2 to the, and this is the. All right. And now I have x squared minus 2x minus 8 equals 0. Factor it, you'll get x equals 4 and negative 2. And we can't have negative quantities in exponential growth and decay. So we cancel that. And we got x equals 4. So yeah, I'll be introducing the rules of logs. Oh, I'm sorry, I remember now, I already did. And that's an example of using them. Okay, so we got that. We got average rate of change. Inequalities. We're already doing inequalities. Where are we doing the inequalities? Well, back with that problem. Well, let's stay here. We're doing inequalities when I say solve 2x minus 3 plus 5 greater than 21. Let's do that. Well, the first thing you have to do is you have to find the numbers that make it equal 21. And that's 16, 8, 3, 11. 11 from 3 8, so it should be those two numbers. Let's check them. -5, -3, -8. Absolute value -8, 8, 16 plus 5, 21. Great. Did I use -5 and get a number bigger than 21? No, I got 21 equals 21. So that number doesn't work. No, doesn't work. And consequently, 11 won't work. So that gives us intervals A, B, and C. And the question is, what works? And I know what works. Numbers bigger than 11 work. These numbers don't. These numbers do. Why? I've done so many. I know the pattern. I know it so well. I don't have to think. You do have to think. And you have to work with numbers. So why don't you put a number in bigger than 11? We can try 12. 18 and 5 is 23. Is 23 greater than 21? I hope you say true. I hope you know if you put 0 in, you get 11. Is 11 bigger than 21? No, false. And if you put minus a million in here, you remember what the absolute value does to minus a million. So that's true. And we're trying to learn how to not butcher the answer. And this is a butchering. X less than -5, X greater than 11. That's a butchering. Numbers can't be in two places at the same time. Notice I use the word and. If you don't put the word or in there, it's really not right. And of course, we've talked about that being this picture. And we're hoping to see everyone write interval notation correctly. So negative infinity. Infinity cannot be bounded. -5. Union 11 to infinity. That's what we're hoping for. That means also, for our purposes, all right, and those are the intervals. These two intervals work. I'm expressing them. What happens if I put an equal sign there? We color in the dots. Nothing new there. We've talked about this many times. And those become brackets. And all I can do is tell you what it is, have you think about it, and if you're not focused right now as I'm talking, okay, catch you another time. That's why I like so many reps. You know, I certainly lose my concentration more and more as I get older. All right, so that takes care of the topic inequalities. Now, what types of problems are we going to be looking at? Well, what I just did there was a sign chart, so to speak, sort of. So let's just say we have 2x squared times x minus 5 times x plus 6, and I want to be greater than or equal to 0. Okay, the ability to do that hinges on your ability to see 0 is a root of that. That's when it equals 0, 5, and -6. And if you'll notice, I didn't use the same stroke of the pen for these roots. I put a dot there, right? And I'm doing that because I know that those exponents, whether odd or even, are going to determine what this graph looks like. And if you want to, you know, tackle calculus, you got to be able to get a little shape out of that. What's it look like? And you haven't had practice with it, so we're starting right now. But, well, I can look at this and I can tell you, when's it bigger than 0? Well, that's going to be true. That's going to be false. That's going to be false. And that's going to be true. So there must be some clues up there that allow me to spot that. And there are. But let's just check it out, see if I'm right, because I make careless errors all the time now. I only got a backup. I got Yasser there to help me. Oh, that was you got me good on the ragtime video. I had no idea why you were putting that up. And then you wrote about the score and whatnot. You know, a little foggy old man here. I had a real good laugh yesterday on that one. That was good. So let's pick a number bigger than 5. Let's put 6 in there. Well, I know that's positive. I know that's positive. I know that's positive. And that's bigger. A positive number is bigger than or equal to 0. True. Let's put a 1 in there. That stays positive. 1 minus 5. Oh, that changes signs. 1 plus 6, that's still positive. And if I multiply these things out, right, because they're multiplication, I get a negative. Is a negative bigger than or equal to 0? Heck no, false. That's why I wrote false. And I know nothing's changing here, whether I pick -1 or positive 1 or -1. It doesn't change this parentheses. -1 squared times 2 is still positive. -1 minus 5 is still negative. And -1 plus 6 is still positive. And that's still going to be false. And I knew that because of the even exponent. All right, so that's the stuff you're going to be practicing. Now, what did this graph look like? Polynomial? What's a 2x to the fourth? 2x squared times x, 2x cubed, 2x to the fourth. What's the end behavior? It's going straight up. And I got a linear cut. So therefore, I've got something that looks linear, quadratic, and then linear again. Linear rates of change, quadratic rates of change at the root. And we'll look at that with table values. But this video is going to go on forever, so we'll save that for when you come back. We'll have another little morsel of deepening our understanding in a particular area. So that's nice. So that's an inequality. And then we've got domain, figuring out domain. Oh, how nice. So let's look at something like y equals, how about we do the ln of x minus 3 divided by the square root of 10 minus x. And I want the domain. Well, I got news for you. You can do that the same way we did the last problem. But instead of looking whether something's bigger than 0 or less than 0, we're simply going to look at intervals and go, can I use that interval or not? And I planted a difficult one here. This is, I think, something that I would hope some of the strongest students could do at the end of the term. Unlikely today, but what are the critical numbers? Well, I actually see 3. I shouldn't have done this to you. Let's do that. All right, let's do that. So what are the critical numbers? 0 and 10. Those are the only critical numbers here, because I'm simply going to say, what am I bigger than 0? Oh no, I'm doing domain. Forgot. Doing it the same way. Yes or no? Can I use numbers in these intervals? Can I use the number 10? Can I use a number bigger than 10? Well, let's start bigger than 10. 100. If I put this into a calculator, would I get a real answer? I don't think so. I don't think I can use numbers bigger than 10 and get on René Descartes. I got my computer on René Descartes. I don't think I can. How about a number like 10? Can I use 10? 10 minus 10 gets me the ln of 10 divided by 0. Can I do that? I hope you say no. I hope you know at this point. You should. You're in high school, you should know you can't divide by 0. And if you don't know that, I'm telling you right now, you should. Maybe you want to make it an important thing to know. Because if you don't, people looking and go, Yep. How about a number between 0 and 10, like 5? ln of 5, yeah, we know that, approximately 1.6, square root of 5. Can I do 1.6 divided by whatever that is? Yes. Yes, I can use that. Can I plug in 0? Am I allowed to do the ln of 0 over the square root of 10? No. This is undefined. We need positive numbers in that parentheses, so no. Can I use -1? The ln of -1? No, I said the parentheses has to be positive, so no. So what was the domain? X values less than 10, greater than 0. You use anything else, you're going to get, I don't know what the calculators say these days, but you're going to say, don't do that. So that takes care of domain. Unit circle evaluations. Now, we've been working with a unit circle and in a way that I've never done before. I've always introduced the unit circle before graphing sinusoids. That was pretty good, 0 circle. So you really need to look at what is a radian. What is a radian and intro to the unit circle. Those videos. Okay, and if you don't, you're going to get lost on what I'm about to do. Okay, so I'm going to look at the sine of 2 pi over 3. Then we use these radian measurements to learn the Lang. What I think we lose from these radian measurements is a sense of where you are on the unit circle. I mean, you can find out easily enough, but I think it gets in the way of learning what a radian is, and that's just as important as this calculation. learning the mechanics of it, is understanding, let's see, that goes about 1.04 times 2, 2.08. That's kind of like the same question. Kind of like, not exact. But I think it's more important that you understand this than that. Putting it together, yes, we've got to do that because it allows us to learn the language. All right, so I will just show you what's on the intro to the unit circle. Is I start with a 60, 60 degree, 60, 60 degree, 60 degree. I bisect it, hypotenuse 1, that's a half, and this becomes root 3 over 2. And I got myself a 30, 60, 90 triangle. And if pi is approximately 180 degrees, halfway around the circle, then pi over 3 is a 60-degree angle, except it's an arc length, right? It's an arc length. So this is how we're going to do things. I just said a mouthful. And that was on your test, by the way. I was asking that on the last test in preparation for moving in this direction. And a lot of people were able to figure that out. Square root of 3 over 2. Well, that's good. Okay, and then I put next to it 0.87, even though I've been asking people to memorize it. All you can do is ask. All right, so I see the sign. I just erased what I wanted to work on. First thing I see is pi. So first thing I do is I draw the arc, the pi arc, half a circle. I break it up into 3 parts. I want the second one because this is 0 degrees or 0 trips, no arc length. And then that's 1 pi over 3, that's 2 pi over 3, and that's 3 pi over 3. And once we get to the place on the arc, that's a 2 pi over 3 arc, roughly 2.08 radius lengths. Radius lengths. I'll keep saying that. If this is a radius, then that's about 1. 1 is about there, 2.08 is about there. Then we drop a perpendicular. And we have the triangle I just drew a minute ago from that isosceles equilateral, right? I've got one of those shaped a little differently, but that's a 60-degree angle, which means that's minus 1/2, that's root 3 over 2, and that's 1. Same ratios I drew over. Oh, it's still there. Picture is still there. All right, and I want the sine of 2 pi over 3 opposite over hypotenuse, which is root 3 over 2. So what work did we do? We did a lot of Pythagorean work in looking forward to these questions. We started, and then we did one with a fraction. Right? That's 1/4. Right, so that's got to be 3/4, and the square root of 3/4, root 3 over 2. Again, repetition, because you might not have looked at what is a radian and introduction to the unit circle, and maybe I catch you with a quick explanation there. More detailed in those other 2 videos. So I'm going to highly encourage you over the break to do yourself a favor and take a few minutes each day. It only takes a minute, 2 minutes, play the video. You know, the first time may take a little longer, but then just refresher. And then you can look at a problem like the sine of, I don't know, let's do 29 pi over 6. All right, and then you're going to say, I hope a half in 5 seconds or less by the end of the term. How are you going to get there? Understanding the concept, drawing good pictures and trig gets good answers. All right, so that's unit circle evaluations. Solving trig equation. Let's do that one next. So what if I said I want you to solve 2 sine x plus 1 equals 0? Well, one thing you're going to learn that in the unit circle, x, that stands for the angle. Oh, somebody here? No, that was just the air. All right, so that stands for an angle. And the sine function, right, cosine function and 1, if you're going to divide this is really height divided by 1, well, that is the definition of sine. It's opposite over hypotenuse. Opposite divided by 1 means the opposite side in the unit circle is representing the sine of the angle. So we can see our heights equal -1/2. A good drawing. There's height of 0. There's height of 1. Halfway right there. Oh, negative, excuse me. Negative, I want to be below the x-axis. So here's -1. So halfway Halfway's right about there, I think. Boom. And if I'm here and here, you got to get familiar with how many chunks is it? Well, that's 1, 2, 3, 4, 5, 6. Oh, 7 pi over 6. 7 chunks of 30 degrees, right? Because this triangle, which I just erased, that's 60 degrees. Well, then that's 30. And what if I put a 30-degree angle? 30-degree angle. Then that would be the 1/2, and that would be the √3/2, and that would be the 1. And that's what I'm drawing here as I make perpendiculars to the x-axis. You're going to have to hear that. Some people misdraw these initially, and we got to correct that right away. All right? Conversation has started. All right, and what's pi divided by 6? Pi divided by 6 in degrees is 180 divided by 6, which is 30-degree chunks. And there's 1, 2, 3, 4, 5, 6, 7. And I hope that you can match that up with 1 period of the sine function. And you're in the 3rd and 4th quadrant. Here's your 1st quadrant, here's your 2nd, here's your 3rd, and here's your 4th. So we will be doing unit circle work. Why? Again, these worksheets are designed to allow you to take a calculus course. And the last few years I was teaching calculus, students were coming in and not able to do that. So we're doing it. We're going to get the job done. And most of my Algebra 1 students last semester had real success with this. So don't panic. It's like everything else. It takes time. But once you get it, it's like tying your shoes. When you were 3 or 4 years old, it took you time to tie your shoes. It was hard. You had to figure things out. I hope you don't still end up having to figure out how to tie your shoes. Unfortunately, in math, some of the gaps that come from those early age brackets continue right up into high school, and we need to change that. All right. What's next? Solving graphing trig functions. All right, I already got some students in class who can do this. There's a few folks who have looked at this critically enough. Something like 6 sine, how about we do x over 8 plus 20. Okay, so we got people getting the range now for the most part. Most folks see 20 plus 6, 26 down to 14. And we've done enough work with the sine function measures height. What happens in the first 90 degrees, the heights of the triangles go up. Heights of the triangles go up. So the first 90 goes up, back down, comes back again. And that dotted line represents the period. So I know I have that shape. I know I start at 0. 0 divided by 8 is 6 times the sine of no walk around the circle circumference. Gets me a height of 20 because I'm right in the middle. And what you'll learn is, what am I multiplying x by? 1/8. And if you take that multiplier and you divide it into 2 pi, that's a shortcut for finding the period. So the period is 16 pi. So it's 16 pi, I'm back to a height of 20. There's my range, right? And if I know that's 16 pi, then I know that's 8 pi. I know that's 4 pi, right? That should sound familiar. 4 pi divided by 8. Well, that's pi over 2. And we've been building all of our functions, all of these questions here. We've been doing the sine functions. And what do? You make 1900 act like pi over 2. And you're making statements like this now. And many of you are doing that, which is great. It's great. Okay, but we want to be able to deepen our understanding, which means look at things a little more depth. So we'll be doing trig equations. We'll be graphing trig equations, solving trig equations. We talked a little bit about derivative, and then the next major topic. I figured we've got 75% of everything that we need in front of us. We're still a week to go before midterm, and we need to look at the next 25%, which we will do. Why do I say we will do? I don't know, because we just did. All right, I'm introducing it right now, whether you realize it or not. So rational functions. A rational number can be expressed as a fraction a over b. So hence, I think 2x minus, how about we do 2x minus 6 over x plus 2. What would that graph look like? Well, first you have to know what fractions look like. Some fractions can be positive. Some fractions can be negative. Some fractions can equal 0, and some fractions can be undefined. Okay, so when you're describing numbers, the first thing you should say is whether it's positive or negative. The next thing you should say is it big or small? And some fractions can be very big. Here's an example. 503 divided by 2. That's a, everything's relative, right? Einstein in the room? No, certainly not at the board. So yeah, as far as our graph, right, a lot of the calculators go from -10 to 10 and -10 to 10, they're boxed in here, and anything that's outside is considered big. So we'll consider that a big number. Right, how about 5 divided by 1 over 200? That's also a big number. This little guy fits into 5 lots of times. This little guy fits into the number 1 200 times. And I'm doing 5 of those. That's actually the number 1000. Big. But also numbers can be small, like 0.05 divided by 73. That's near 0. So that's going to happen. All the things that I just talked about are going to happen in this one problem. And YouTube is got hundreds of these. Right? You can go graphing rational functions. You'll get problems like this. You'll get problems like 2x minus 6 over x squared minus 4. Right? And you'll learn the rules that govern how to do. I'll do both of these. So what do I know about this one? The first thing I see is -3. 0 gets me -3. The next thing I see is -2 is undefined, so I better move that over here. 0, well, where to put it? I don't know. We'll put y equals 2. I can see asymptotic behavior. I can see asymptotic behavior, y equals 2. I can see that it's got an x-intercept of 3, 0, so 0, -3. I can see that. I can now see that x equals -2 is undefined. I can see the trajectory that's going there, and therefore there's going to be sign changes here because this is to the first, that's to the first. I'm done. You can't do that yet. I know you can't. Right? But you're not going to be able to until we start the discussion. We just started the discussion. Right? And if I wanted to do this one, well, first thing I got to do is factor x squared minus 4. Which is x plus 2, x minus 2. And so now I have 2 undefined situations at 2 and -2. The fraction's undefined there. I can see that the fraction going back to 2x minus 6 over x squared minus 4, if I put 0 in, that cancels and I get 1.5 or 3/2. So x equals 3/2 is the y-intercept. So I guess I should put a 0 there. I know that this thing goes to 0 asymptotically, it goes to 0, and I think it goes in this direction, which means I'm going to get sign changes everywhere. So I'm going to go from positive to negative, which means that I got to have an x-intercept here. Got to be one. Let's see now. X equals 3. It's actually over here. So I butchered that. Got to come back to that. And I'm going to get sign change here. So which problem am I looking at? Got to remember. Okay, so I've got that. So let's not put things in until we're sure. So 3 is here. So therefore, I'm going to be, as I put huge numbers in, it's definitely positive. So this is a little tricky here. And that's going to go back to 0. As these numbers get bigger, right? Let's put 10 in. If I put 10 in, I get 14 over 96, I believe, which is close to 0. But it's positive. Right, now I definitely have an x-intercept at 3. So now the question is what's going on here? So I put a 0 in, and I don't have any more x-intercepts. So now I'm back to the topic at hand. So it's got to do that. And then there's got to be a sign change, and I don't have any more x-intercepts. So I think I'm finally onto it. Talking to you too close to the board here, had a momentary lapse, but I think we're good now. So we're gonna be learning how to identify that it's going to zero just from the get-go. Just from two right here, just from there. You know, I knew that went to zero on both ends. I want you to know why. When you come back from break, we'll find out. But if you want to get a jump on it, your education, don't be afraid to look at a video, a rational function, because it's going to take you several days to process, you know, how to find an x-intercept. I remember the first time I looked at these, I was clueless. Yeah, but you can always go back to point analysis. And so we'll be starting with that. Limits. Well, that's really what I was talking about here. The limit as x goes to infinity of 5x minus 2 over 4x plus 7 is 5/4. How could you check that out? With maybe some numbers. How about we go to infinity? How about we put 100 in? How about we put 1,000,000 in? So I have 5,000,000, 6 zeros, minus 2 over 4,000,000, 1, 2, 3, 4, 5, 6, plus 7. And if you want to approximate, I don't think you're going to mess around with the 7 and the minus 2. 5,000,000 divided by 4,000,000 is a 5-to-4 ratio. So just took what, 20 minutes, 30 minutes to put the next 25% of what we're going to work on in front of you. Why are we doing it that way? Because we can. And if we spend 2 months on those topics, 2 months, a little bit every day, I think it's going to serve us better than do a week on rational functions, move on, not see it again until the final exam, and watch your knowledge slip away. All right. How are we going to keep it from slipping away? We're going to do it every day. That sounded like a poem. Slip away, do it every day, something in there. All right. So that was good, I hope. Maybe. Okay. See you in a couple hours.